Hello everyone, this is Tianyi. Thanks EAI conference community to bring me here and give me this chance to present my paper. As you can see, this paper brings up a low-cost software-defined radio system for unmanned aircraft vehicle spoofing. Recently, the booming demand for civilian unmanned aircraft vehicles, which stands for UAVs, brings increasing security concerns at the same time. The biggest threat is that the uncontrolled drones could crash into aircraft, endangering passengers and the pilot. Spoofing a UAV is generally conducted through spoofing of its GPS module. There are widespread research interests on the vulnerability of UAV's GPS network. In this paper, a low-cost, software-defined radio platform has been built utilizing the vulnerability of UAV's GPS network. With this platform, three spoofing strategies has been provided and tested. Simulation experiments verify the effectiveness of those strategies, which can also be applied to hack into UAV's GPS network and take control of them. First, let's talk about what exactly are drones. Drones, also known as unmanned aerial vehicles or unmanned aircraft systems, are more advanced version of the model airplanes hobbyists have flown for decades. They came in airplane and helicopter varieties, sometimes with 8 or more spin rotors, while drones are typically piloted from the ground by human. With the radio controller, many are also capable of autonomous flight along program coordinates. Some hobbyists buy drones for the sheer joy and challenge of flying an object in the sky. But the biggest thrill for many is capturing spectacular, high-quality photographs and videos from an area vantage point. Unmanned aerial vehicles, which stands for UAVs, has been used by the military for a very long time. But now, as the market of civilian drones increase, as well as the safety concerns along regulators and law enforcement agencies, which worry about drones' collisions with aircrafts to crash into crowded stadiums or any other buildings. One of the biggest safety concerns about drones is that they could collide with aircraft, endangering passengers and pilots. We can see in 2013, the German chancellor is taken aback by a drone that crashes 2 meters away from her at an election event. In 2016, the pilot of the Boeing 727 flight from Geneva has been struck by the unmanned object shortly before it landed. What if someone on the ground could hack the drones and turn them into their device, making them go to a different place along with a different path? That could be a disaster. Some drones like DJI are developing software that will prevent people from piloting their drones into restricted airspace. We can also build our customized no-fly zone via GPS spoofing. We find that the navigation system of these drones has a variety of sensors, but at the very bottom is the GPS unit, and most of these drones has been used in the civilian airspace has a civilian GPS unit, which is wide open and vulnerable to this kind of attack. So, if we can commander the GPS unit, then we can basically spoof the false navigation information of these drones. Therefore, we did some research on the GPS spoofing to the UAVs. The first step is to generate the fake GPS signal. That's why we need to analyze the GPS positioning principles. GPS is a satellite-based navigation system. It uses a 1.5 gigahertz digital signal to send data to the receiver from each satellite. Then receiver can calculate its accurate range from the satellite, as well as the geographic position of the satellite. The geographic position is the location on the Earth which connected to the satellite. Therefore, a line of position on the Earth can be established and can be clarified like this. And here, this is our SDR platform, which is a low-cost software-defined radio-based GPS signal architecture test set by USRP radio and the GPS signal simulation toolbox. Here, the SDR refers to the technology wherein software modules running on a generic hardware platform are used to implement radio functions, where the USRP are computer-hosted RF transceivers used for development and exploration of software-defined radios. The USRP includes a 10 MHz frequency standard as well as input for the external reference clock. This GPS signal architecture software can produce any custom GPS scenario data files which can use the USRP to produce GPS signals. The next step is to combining the NI USRP with LabVIEW are going to give us the ability to construct our GPS signal. And taking Unmanned file, ephemeris file, and coordinate and other parameters like the IQ rate or the carrier frequency and the gains as the input of the GPS module and send the simulation result via the USRP. The sample Unmanned and ephemeris files are already included in the installer. We can also find the updated files from the official website, and it also can be downloaded directly. The GPS signal can be generated, which will carry the information of location that we need with an intuitive graphical user interface. It's simple to generate the fake GPS signal from all over the world. To reduce the error factor, for example, the multipath of the GPS receiver, our experiments were conducted in a pretty wide open area, and the experiments were carried out in 3 different scenarios based on the hovering, waypoint flying, and return to home mode. First, let's check out the first test scenario, which is the trajectory spoofing. In this scenario, the aircraft has a preset flight path instead of being hovering in the air. In waypoint mode, the aircraft can record a flight path and it will fly in the preset path repeatedly while you don't need to control the aircraft, right? And the flight path can be saved and reapplied for the future use. In this mode, aircraft can fly along its recorded path to the destination. If we need to change its flight path and make it fly away from the original destination, we should send an opposite direction GPS signal. Once the aircraft receives the fake GPS signal, it will adjust its flying path according to the fake GPS signal. The second scenario is return to home spoofing. The DJI Phantom 3 standard has the return to home function. Just as its name implies, the return to home function or the return to home procedure will bring the aircraft back to the last recorded home point. The home point is the location at which the aircraft takes off, right? And once launched return to home function, the aircraft will firstly ascend to the return to home altitude, then return to the last recorded home point if a GPS signal is available. Therefore, the flying aircraft can be captured utilize this return to home function only if we know its home. We know its home point, right? If the drone's home point has been exposed, it's capable to generate the fake GPS signal of the same location through this self-built SDR platform to make the flying aircraft think it already arrived the home point. As a result, the aircraft will land on the location that we set already. The third test scenario is the no-fly zone spoofing. Unmanned aerial vehicle operators should abide by the regulations from self-regulatory organizations such as the International Civil Aviation Organization, which stands for ICAO, or the Federal Aviation Administration, which stands for FAA, and their local aviation authorities. For the safety reasons, flight limits are enabled by default to help users use the product safely and eagerly. All the no-fly zones are listed on the DJI official website. When operating the aircraft or operating the UAVs in P mode, the altitude limit, the radius limit, and the no-fly zone work together to bound the aircraft. In A mode, the aircraft cannot exceed the altitudes of 400 feet. If you fly out of bounds, you can still control the aircraft, but you cannot fly it further. The GPS-dependent systems are ubiquitous in the current positioning and navigation applications. However, the GPS signals are vulnerable to in-band interference because the GPS signals can be extremely weak to the broadcast signals of wireless channels. In this paper, we analyzed the vulnerability of GPS module in UAVs and brought up a GPS spoofer based on a low-cost software-defined radio. The aircraft was successfully get spoofed in 3 different real-world scenarios, which stands for the trajectory spoofing and the return to home spoofing and the no-fly zone spoofing. For all those 3 test scenarios, The testing aircraft get spoofed in a short time. The time interval between the fake GPS signal generating and aircraft getting spoofed is about 2 to 3 minutes. Furthermore, the flight path becomes more precise and smoother after generating several fake GPS signals from different locations at the same time. Due to the limitation of the testing space, the testing aircraft must be operated in a relatively low speed. All the test results are subject to this condition. However, not all the aircrafts are flying at a relatively low speed. More work will be continued and conducted on a high-speed aircraft spoofing, and also more work will be started on the anti-spoofing in the future work. And I think this is pretty much about my presentations. And thanks everyone for your attention.